Hi, I'm Gabriel and I'll be presenting my team's work on the privacy assessment of very large datasets. INEP is the federal government agency in Brazil responsible for the country's educational censuses. In Brazil, a transparency law from 2011 established a tradition of governmental data transparency. But since 2018, the enactment of a new privacy law restricted the release of data on individuals. As a data curator, INEP has now to carefully balance those two principles, and for doing so, it is crucial to identify meaningful threats. In order to do so, we were tasked with providing a theoretically solid solution that could be, at the same time, flexible, scalable, and explainable. Our contributions include a refactorization of privacy attack models, a new way of applying the quantitative information flow framework, and an illustration of both flexibility and scalability of the QUIF framework. On the literature, one can find several privacy attack models, usually classified according to the type of information sought as membership inference, re-identification, or attribute inference. Re-identification in particular is usually also classified according to the adversary's prior knowledge and target as the attack models known as prosecutor, journalist, and marketeer. Instead, we propose a new classification based on three orthogonal axes: one for the information sought by the adversary, another for the adversary's target, and a third axis for the adversary's access to datasets. Given our orthogonal classification, we devised 12 distinct privacy attacks, including those already found on the literature. More interestingly, our factorization covers new scenarios such as attribute inference attacks on longitudinal collections of datasets, which generalize all the others. I will now briefly introduce the quantitative information flow framework, followed by an example. One of the main advantages of the QUIF framework is that it separates into three distinct entities: the adversary's knowledge, which is modeled as probabilistic distribution on the secret values and usually called prior, the description of the actual leakage of information being exploited, which is modeled as Bayesian reasoning to produce a hyperdistribution from the interaction between the channel that describes the system and the prior, and the adversary's intentions and capabilities, which are modeled as a gain function. As an example, assume our adversary is about to meet someone for the first time and is trying to guess the native language of the person. The adversary assumes the person is equally likely to be any one of the four in the dataset shown here, which is accessible to anyone. We can compute from this dataset the prior on language, which corresponds to the adversary's knowledge before seeing the person. Clearly, the adversary's best guess before seeing the person would be German. But if the adversary sees the person before guessing, then both gender and age are leaked. The full procedure for converting the original dataset into the hyperdistribution is presented in the paper. But from the hyper shown here, we have four possible observations with their corresponding probabilities given by the outer distribution. For each observation, the corresponding posterior probability gives what the adversary has learned about the language from that observation. For instance, there is a 50% chance the adversary will see a young man, and from that observation, the adversary will learn that there is a 50% chance of the language being Portuguese or German. But there is one missing piece here, the gain function. Suppose the adversary can be described with a gain function that yields $4 for a correct guess and 0 for a wrong guess. Before the leakage, the adversary's best guess from the prior would be German. In this case, the expected gain would be of $2. But after the leakage, the expected gain is computed from the hyper. In this case, the expected gain would be of $3. In order to instantiate QUIF for the INEP scenario, we assume the following. There is a longitudinal collection of datasets and a persistent attribute of unique identification for each student. The adversary's prior knowledge includes the access to all the datasets considered and hence to their respective distributions of secret values. For longitudinal attacks, we select one of the datasets as the focal one, in which the attack will be performed, while the other datasets are considered to be auxiliary information. Furthermore, the adversary assumes that each individual holds only one record on the focal dataset and at most one in each other dataset. The channel is a rewritten version of either a unique dataset or an aggregated dataset derived from joining the focal and auxiliary datasets. Moreover, we consider the adversary also mines auxiliary information from other sources to proceed with the attack, for instance from social media. The attack is then performed when the adversary combines the prior knowledge with the channel and applies Bayesian inference to produce the hyperdistribution. For deterministic attack, the threat is quantified as the proportion of individuals whose secret values can be inferred with absolute certainty. For probabilistic attack, the threat is quantified using the Bayes vulnerability function, which corresponds to the probability of inferring the secret in one try. Finally, the leakage of information is quantified by either the ratio or the difference between the adversary's prior and posterior knowledge. This figure schematizes and generalizes our attack models in QUIF. At first, the adversary has access to the focal dataset, say the school census of 2014, from which the adversary derives a prior knowledge. Moreover, the adversary has access to the datasets for the school census of 2015, 2016, and 2017, and can also gather information from social media. Once the attack is performed, the adversary may become capable of re-identifying individuals or inferring the values for sensitive attributes, from medical conditions to economic status. So here we have some details about the INEP datasets we have analyzed. For all of them, the only disclosure avoidance methods applied by INEP to protect the privacy of individuals were the identification, which consists in the removal of obvious personal identifiers, such as name, and pseudonymization, which consists in the substitution of such obvious personal identifiers for artificially created ones. In order to fulfill the assumption of only one record for each individual in each dataset, we have treated the microdata by randomly selecting only one record for each student with the same unique pseudonymization code in each dataset. For attacks on the school census of 2018, we chose the 11 attributes listed on the left column and performed the analysis for all the 2047 non-empty combinations of those attributes. For attacks on the longitudinal collection from 2014 to 2017, we chose the 3 attributes on the top of the right column, which may change over the years. In both cases, we have selected the disability status and the use of public school transportation as the sensitive attributes for attribute inference attacks. So here we have all the results for the 2047 non-empty combinations of QIDs for the school census of 2018 for both deterministic and probabilistic measurements of privacy degradation. On the horizontal axis, we have the size of the set of QIDs used by the adversary, and on the vertical axis, we have the adversary's success. The horizontal line with a label a priori represents the adversary's knowledge before the attack, that is, the information obtained from just the dataset itself and its distribution of secret values. For instance, with only day and month of birth and school code, almost 31% of the students could be re-identified, while 95% could have their disability status inferred and 85% could have the transportation method inferred, in all cases with absolute certainty. By adding only the year of birth to the set of QIDs, those numbers would increase to 81%, 99%, and 97% respectively. For the longitudinal attacks, the analyses were performed using only one set of QIDs, namely city of residency, school code, and educational stage. Here we present the results for the deterministic measurement of privacy degradation. With only 3 seemingly innocuous QIDs and access to up to 3 auxiliary datasets, we can verify that large proportions of students are vulnerable to attribute inference attacks which result in absolute certainty by the adversary. The same goes for the probabilistic measurement of privacy degradation, particularly when it comes to re-identification attacks. Here, the percentages are the probabilities of successful inference in one try, measured by the Bayes vulnerability function. The prior success for attribute inference attacks is highly influenced by the skewness of the distribution of secret values. In this project, we have learned the importance of reinterpreting and reproducing results from the literature in order to convince stakeholders of the existence of privacy vulnerabilities. A literature review on its own is not convincing for politicians or the public in general, for instance. Moreover, the use of rational adversaries such as that model by the deterministic measurements of privacy degradation were essential on this task. On the technical and scientific aspects, we have learned new ways to use the McIver framework, a clear benefit for basic scientific research as a result of engaging with a real-world problem. For future work, we envisage the use of QIDs instead of a persistent attribute of unique identification in the process of aggregating longitudinal data sets. Furthermore, we envisage the use of the channel capacity, which can estimate the maximum privacy risk over all reasonable adversarial models. The software developed for this work is publicly available on GitHub. Given the vulnerabilities reported in this project, INEP has recently removed the microdata from their website. Instead, INEP is now providing aggregated statistics as a temporary solution. Thank you all for your attention, and special thanks to my co-authors.